Wow, futures. Thank you so much for coming and listening to me talk about futures. I've got a rather grand proposition here. I'm going to be making the case for algebraic promises. But don't worry about that. I'm sure there's two questions in your mind. Question number one, quite rightly, is what is a future? So a future is a wrapper for a value that really cares about time. And I'm not just talking about like a date or a way of representing time, but something that you actually have to wait for. And when it comes, it might have succeeded or it might have failed. I'm not talking about a bus. These are things like promises if you've seen them before. And the second question I imagine on everybody's minds is, how does he think he can get away with such an awful pun as Back to the Futures? Well, reason number one, I have no shame. And reason number two, technically works. So whilst the functional JavaScript scene is fairly new, futures have been around for only 3 or 4 years in JavaScript, but they actually have a very old history. So the IO type in Haskell is actually a kind of future, and that's been the way of doing interactions in Haskell for the last 20 years. So technically, we can go back to the futures. So, what I don't want to do, that's exactly what I want to do. What I don't want to do is leave anyone behind. So I've started the presentation with a little bit of a need to know section. So this is what I would ideally like people to know. So this is a common baseline so that we can press forward together. So I'd like everyone to know JavaScript tonight. We've kind of got mostly JavaScript guys here. Cool. I'd like people to have some experience of the map function. If any of these, well, certainly the second two, map and promises, if you don't know them, I can do a really quick crash course on them. So I'm going to ask for a little bit of audience participation, which isn't great, but so can I have a rough show of hands for people who think they know what map is, who've kind of seen map there in JavaScript? Everyone comfortable with map? Actually, a pretty high level of comfort with map there. That's really good. Adam's not. Okay. So
I don't even like JavaScript.
Yeah, okay. Adam doesn't like JavaScript. He's not my priority. So I will talk about what we don't need to know. Okay. So we don't need to know functional programming. I know I name-checked Haskell already. I'm really sorry for doing that 1 minute into a presentation. This is about JavaScript. I love JavaScript. I love functional JavaScript. I don't expect you to know a strongly typed functional language. I don't expect you to know category theory for mathematics. And I don't even expect you to know any other async techniques. So events, observables, anything like that, that's not important today. We're just comparing futures and promises to give you a fair go on whether futures is something you might want to try out at work or in your hobby programming. So, oh no! Okay, well, there we go. So, yeah, map. So a little refresher on map. So map is a higher order function, which basically means it's a function that takes another function. And the function that you give it is then applied to every item in the list. So let's say, for example, we have a list with some numbers in, 1, 2, and 3. And I call map on that list. Function I give to map then gets applied to each item in the list. So for example, if I got this function up there, add 1, is everyone cool with the arrow syntax? Yeah, I've done the kind of more traditional pre-ES6 version there for people who are not used to the arrow syntax, but I've got add 1, which takes an x and adds 1 to the x plus 1. So if I call 1, 2, 3 map, add 1, the result should be 2, 3, 4. Pretty simple. I've also got an example there where we've used an anonymous lambda functions for the same thing. So that should catch you up on map. Then we've also got promises. I know there's a fairly kind of niche famous article on broken promises, which is all about futures, saying that futures are a better version of promise. I don't think that's strictly true, but there you go, you've got your broken promises. So, just like futures, a promise is an object that wraps an eventual value, something that you're waiting for that will come to you. It represents the eventual completion or eventual failure of some asynchronous operation. So that might be sending out to an HTTP server for a bit of JSON, might be reading a file from a file system. I hope you like that example, I've used that one a lot. as well as adding one to things. I've used that one so much today. So to create a promise, you've got new promise, so it's kind of a little bit objecty there. You pass in a function for, takes a function for resolve and reject. So you then start your underlying asynchronous operation. When it succeeds, you call that resolve function with the success value. When it fails, you call the reject value. You call the reject function with the failure value. Okay? So when you're using promises, it looks a hell of a lot like that second example. There's a lot of doing something that will take some time, and then there's a hell of a lot of dot then, dot then, dot then, dot then. As you kind of chain together everything that happens after this initial bit of asynchronicity. So are we kind of feeling cool with map and promise? We can kind of press on. Okay. Really, really, really crash course on what matters to me about functional programming. So functional programs, and again, I perhaps should have asked, how many of you have kind of done functional programming, seen functional programming, heard of functional programming? Should we do hands? Should we do hands? Again, really, really great numbers, fantastic. So yeah, what matters to me in functional programming is that programs are composed of smaller programs, which eventually you get down to these kind of atomic values, which are functions and values. Okay, so values you're used to, things like numbers, strings, objects, arrays. Functions you've seen, this add one function, as I said, this will come up a lot. Even things like this, like a reduce, a slightly more complex example of a function. So what I'm going to be doing is introducing a couple more types to really help you get a handle on what futures are. In particular, I'll be introducing the future type, so the clue's kind of in the title there, and I'll be showing you the either type, because it's a way of really unlocking some of the superpowers of futures. This also means that we're going to need to make a little bit of a start on a concept called type classes. Okay? So I'm not going to go into too much detail because it pulls us down into a kind of category theory rabbit hole. I don't want to go really, really deep into them. But if any of you have done any object-oriented programming, it might be useful to think of them as interfaces. So the type class will generally come with one or more functions, and in order to be a member of that type class, you have to implement those functions. Don't worry, it says there, don't worry. We're mostly just naming them and moving on, okay? So, type classes. This kind of rainbows and unicorn stuff, this isn't just to make you feel happier at this point, although hopefully it is distracting you from some of the words that are going to come up in a second. This is actually the logo for a kind of movement called Fantasyland within the open source JavaScript community. This comes from a comment Dominic Demicola made about promises, a comment thread way back in the day, where he said, you can go and live in your typed language's Fantasyland. We're never introducing those changes into promises, into the promises A+ spec. And of course, the monadic things that we were asking for didn't end up in the promises A+ spec, but we did decide to go and live in a Fantasyland. So this algebraic specification was created. It's kind of cribbed from Haskell, but it's not Haskell. Again, the people working on algebraic typed functional JavaScript, like me, are passionate about JavaScript. And it's got a very idiomatic JavaScript feel. It's got some different terminology for some of the things you might know from Haskell. So I wanted to start you with a couple of the type classes for a type that you already know. So you all know what a list is. So a list is a container for 0 or more values. When there's more than one value, the order matters. And the type classes, a couple of the type classes involved in lists are functor and foldable. So just keep those in the back of your mind. They'll come up in a minute. Future has functor, foldable, and So, yeah, what I'm not going to do today is a monad tutorial. That's a topic that nobody needs to get into. Again, I will touch very lightly on it and then I will leave it alone. And either, I kind of name-checked either in the previous slide. That's also a functor, that's a monad, and it's also a bifunctor, which sounds pretty cool. So, functor. Any type which implements the function map, and it's not quite the exact terminology, but this is broadly what we're getting onto. Any type implements the function map is a functor. Okay? And what map does, if you think of what map does to a list, is it's a function that's run against every element of the list. So when map is applied to a different kind of functor, it runs the function you give it to every element in that functor. Now, in the case of a future, probably only one element in it. Probably just that one value that you're waiting for to come back from HTTP or from the file system. When you call map on it, it'll act on that one value. Foldable. Types with a fold function, you can have a situation where all the elements of the structure are folded together into a single value. So you probably know this as reduce in JavaScript. Monad has two functions in the Fantasyland specification. They're actually kind of inherited from other types, but so you've got chain, which allows you to combine monads together, and you've got of, which lets you turn simple values into monads. And then this will come up very near the end. Try and remember it though. We've got bifunctor. Bifunctor is a type that can hold two values and has several functions for changing those values, such as left, right, and bimap, which works on both values. But you can kind of put that in your brain for a minute. Because I want to talk about a library with a really cool logo. This is called Fluture. I think it's called Fluture. Might be called Fluttery or something like that. It seems more likely that it's called Fluture. It's got butterfly, so it could be Fluttery. Anyway, this is the one I really recommend. There's a few different ways of getting up and running with Futures on NPM or GitHub. I recommend Fluture because of the great documentation. It's got some links to some great wikis and really good articles, a couple of good videos. It's also measured as having the highest performance of all the Future libraries and actually exceeds the performance of some Promise libraries. So that's really good. I recommend you check it out. So, we're kind of at a point where we can actually start talking about futures. I think we've done the groundwork and we can start talking about this type. So if you remember, I showed you a slide about how one might want to create a promise. This is how you might create a future. It's looking really similar so far. Got that new keyword there, new future, reject. Okay, that's the opposite way around. So when you're making a promise, it's resolve, then reject. When you're making a future, reject, then resolve. In futures, error case always comes first because there's no way of ignoring the error case in futures. Just a design decision, a really sensible design decision. At this point, you would do all your async. You start your underlying process, whatever that might be. When it comes back with success, you call resolve. When it comes back with failure, you call reject. So all really similar so far. Here's a concrete example of a little bit of NodeJS that I have converted to use a future. So we've got read file. As you'd expect, it takes a file name as the argument. We then, go too far. We then instantiate our future with reject and resolve. We call fs, file system, .read file. If you don't know Node, I don't think it should be a big problem. I think the concept of reading a file from a hard drive should be pretty straightforward. UTF-8 is just the encoding, it's just something you need to provide. So it takes the file name, takes the encoding, it's got a node style callback with error data. If there's an error, I reject, providing that error. Elsewise, a result. And then the rest is just boilerplate that we all know about. So, once you've got your feature, maybe you've made it yourself, maybe you're lucky enough that you're working with a library that exposes the features API, you then probably want to do things with the value that you've waited for. I mean, you've waited for it, you've fetched it from somewhere, you might as well do something with it. And the really cool thing is this is where those type classes start kicking in. So a feature is a functor, if you remember that. And as a functor, it can be mapped. So what it can do is, say I've got a feature of 2. I can map that, throw in my add1 function, and what do I get out? I get out a feature which holds the value 3. So I've run a transformation, or I have prepared a transformation for that feature. It's a slight difference. Get to it in a minute. Same with the error state. So if your feature is holding a fail state, in this case, it's holding a string describing the type of error, we can map over that as well. In this case, it kind of ignores what you put in this map transformation and just carries on returning a feature with the content saying an error. So, how do you get stuff out of a feature? Well, to finish off a feature, you have to call fork. What that does is it actually begins the computation. So the point at which you call fork, that's when that underlying async process kicks off. Okay? So I make my feature, I do any sorts of transformations I want, and then I call fork. So as I said earlier, features are really, really keen on making sure you handle your errors. Most feature libraries will throw errors if you don't provide 2 functions, and you have to provide an error callback. The error callback's first, it's very important, and a success callback. The success callback is second. And these callbacks let you handle basically what comes out of your feature and all the subsequent transformations. So, come back to the whole monad thing, unfortunately. It was only a matter of time. So I said that monads have a chain function for combining with other monads. So in the case of features, the chain function will take the value wrapped up in your feature. So maybe you've got the number 2 in there, like we've had a couple of times. But it must return a new monad. Okay, so unlike map, where we were able to take 2 and return 3, if we called chain, we wouldn't be able to do that. 3 would not be a valid return value. It would have to be a new monad. Okay, so this can be used to chain different asynchronous actions. Okay, so maybe you need to fetch something from HTTP, and then you have to fetch something else from a different endpoint somewhere. That's when the use case for chain comes in, when you need to do something asynchronous, and then another thing that's asynchronous. So I'll give you a code example here. So I've got read file that I specified for you earlier. I'm reading a file called version.txt. Now, this isn't the way to do software versioning, just to be really, really clear, especially if you're in JavaScript. There's this thing called package.json, it's got Semver, it's way better. But for this example, we're loading version.txt. This is a text file with a number in it. So, as you can imagine, we're going to do that thing we always do. We're going to increment our number, add 1 to it. And then, chain comes in. This is where we take our new version number and we do write file back to version.txt with that new version number supplied. So, now we need to fork it. This tells the feature to begin its computation. Got a console error here for the error case, could not save, and give the reason why. And a success case, saved new version number. That is a working program. Now, it probably needs some imports at the top because this is JavaScript, but composed from just a few tiny parts, you've got a working, semi-useful program. For completeness, that's what write file would look like. kind of encased in that node style callback, write file of the future. Everyone cool with that?
Yes.
Yeah? Cool. So it's a little bit more fiddly. It appears a little bit more fiddly than promises. With promises, you'd be able to do the same thing, and you'd just be able to kind of then, right? It's a lot easier, dot then, dot then, dot then. This forces you to be more precise. But so far, you know, what's the benefit? What's the benefit? Yeah, sorry.
So calling the dot fork on the end is like putting the chain on the right hand side of the left pointing arrow in the middle of the do block.
Precisely.
That's okay.
So let's start getting into the actual benefits of futures, because so far they seem like a slightly more fiddly promise. Okay, so we've seen how we can use chain to call two futures in series. Sometimes there are common use cases where you need to call stuff in parallel. So maybe there's a bunch of stuff that you need to fetch at once, or just a load of asynchronous things that just don't depend on each other, and you don't want them kind of blocking each other. So here's a technique for doing that. This is specific to the future library, and I'm going to talk about the problems with that in a moment. So you can do future.parallel. You can pass in a concurrency limit at this point. So this basically tells it how many futures to keep in flight at once. This means that you don't overload the system that you're calling out to. If you have no concerns about that, you can just use the number infinity here. The second argument will be an array of futures. And what comes out of parallel is a future that contains a list of the results from all those other futures. Okay, so I'll just go over that one more time. What goes in is a list of futures. What comes out is a future of a list. Okay, so you can see the types got kind of knocked over onto their sides. Okay, it's got this built-in rate limiting. So in this instance, where I've set my limit as 5, I've got my futures as a couple of read files. The result will be contents of file 1 and contents of file 2. Yes?
Is that sequence?
This is not in sequence. This is
No,
in
no,
parallel.
is that the same as sequence operation?
Yes.
Yeah.
Yeah, I'm going to get right to that.
Okay.
Cool. So, I kind of said I was feeling a little bit problematic about the fact that parallel is specific to the future library. In fact, I kind of almost prepared in advance all the functions that I thought we would be using today. I talked about chain, I talked about map, I talked about ob. I didn't mention parallel in there anywhere. So what's the deal with that? Well, here's an interesting quote. Avoid success at all costs. Dr. Simon Peyton Jones. So what he doesn't mean, what he's not trying to do, this is the creator of Haskell, one of the creators of Haskell, one of the maintainers of its compiler. What he never means by saying this, and it's a little programmer joke, I guess, he doesn't mean that he's trying to avoid success. That's not what he means. He's not scared of success, he's not worried about giving away his cool language, he wants success. But what he doesn't want, this part of the sentence, success at all costs. He thinks that is something to be avoided. What is success at all costs? Success at all costs is succeeding at the expense of something else. Okay? In the case of functional programming, I think in Dr. Simon Peyton Jones's case, he doesn't want to succeed at the cost of his principles. Okay? And I think this instance where we've used a parallel function is perhaps a case of us succeeding at the cost of our principles. Because by using a function that isn't part of a type class, I've now locked myself into the library future. I've failed to learn something as well. So by seeing this really useful, really successful parallel function, I now haven't had to learn how to really do it. And how you really do it is a little bit more complex. So how you might really want to tackle this is to use a more generic function called traverse. Traverse will let me do exactly the same thing. It will let me take a list of futures and turn it into a future of lists. Lets me do that 90-degree turn. But what it does it in a way that works for any functor and monad. And that is powerful. And the reason that is powerful is because at that point, it's not an API, it's a grammar. The beauty of learning small, reusable pieces that can be combined in different ways is the core of functional programming. At the point at which you start flooding your API with 100 functions, 300 functions, 4, 5, 6 big libraries, you've lost that elegance. You have succeeded at too high a cost. If you can build your programs from the smallest components, from the smallest grammars, and the infinite complexity rolls out from there, you've succeeded with principles. So, I'm not going to have time tonight to actually show you some of the better ways to do parallelism, but just let that one stay there as a little nugget in your minds. So, what I do want to talk about is what I've termed, I thought about this one a long time, a really good futures use case, okay? And this is error tolerance. So this one came up at work, okay? So we built Habu. Oh, I realised what slide got missed at the start now. I'm going to go back a second. So the slide that got missed was a slide about who I am. So I've been trying to take you on this journey with futures, and you're like, who is this guy? What is his deal? So I will share the slides at the end. I'm Mark Withers. Nice to meet you. I work for a company called Habu. We do co-working software. We're based here in Bristol. There was also some other stuff. There was stuff about my beard. I keep some parrots. I had some pictures of parrots. I don't know why it all got lost. It's got my kind of GitHub and my Twitter. So just pretend you saw that, and it all happened, all right? So we built Habu on AWS Lambda, which are serverless functions that exist in the cloud, someone else's computer. The really nice thing about this is we don't have a single EC2 instance, we don't have to manage any databases. The drawback of this is that you have to have all your useful work done in a Lambda function within 5 minutes at most. So we have a few kind of end-of-month processes that take longer than 5 minutes. So we didn't want to just spin up an EC2 instance and write an Express server, that would be too easy. So we wanted to keep it all hosted and keep it all managed. So we came up with a queue system. So we used DynamoDB streams as our kind of queue. And so what the queue does is it allows you to put a whole load of jobs in, like way more than a single Lambda function will be able to handle. And then they kind of, just like a real queue, like at a nightclub or whatever, then as the queue is there, the doorman lets a batch of 5 in, closes the door. That's how a nightclub works, isn't it? Yeah, and then once they've all asynchronously resolved, he opens the door and lets another batch of 5 in. I'm pretty sure I haven't been clubbing in a long time, so I remember it being a bit like that. So this is what happens in Habu. So we've got our big list of jobs. In our case, it's kind of end-of-month billing, where we charge people on behalf of other people. And we want to take a few at a time and resolve them. So I built that using promises. I thought, oh, this is good. I'll take my batch of 5 jobs. I'll put it all in a promise.all. Oh no, some of them failed. One of them failed. If one fails, they all fail. That's a bit of a problem, because I want to know the successes and I want to know the failures. And for the successes, I want to write them back to the DynamoDB table and say, succeeded. And for the failures, I want to increment a retry number and leave the status as ready to go, so that they go back to the back of the queue and they try again later. So the fact that promise.all failed them all is a big problem. Okay? So there's a promise library called Bluebird that provides a utility function for handling this situation. I was like, oh, brilliant, I used that in my last job, that would be great, I'll look it up, it's called settle. So I go to the Bluebird website and I look up settle. It's not there. It's the API's version 3 now, it's called something else. I've legitimately forgotten what it's called. But that's kind of the point, right? It's got a specific vendor locking style API. If you forget what it's called, you forget what it's called. Anyway, I implemented it with Bluebird. It worked really nicely. My colleague Sam said no. He said we've got these handlers that we wrap around our Lambda functions, and I don't know if you noticed, but they're using generic A+ spec promises. I don't want them tied to Bluebird. It's just one implementation. I was like, oh, okay, maybe there's a better way. So I thought, well, I've seen these futures things. I did a bit of research on them before, and I thought, well, let's try futures. So I tried future.parallel, checked my 5 jobs in. One fails and they all fail. That's a problem. That's a problem, right? How do I resolve that? How do I make them all look as if they've succeeded? And with futures, there's an actual way to do it, an actual sensible way, using these type classes, using this grammar, using this small, simple API. There's a way of doing it. And this involves the either type. So quick aside onto what an either is. An either is going to feel a lot like a future. Okay, an either is a wrapper for a value, which can either be one thing or another thing. It can either be left or right. By convention, we generally put the success value in the right-hand side of an either. Think of it as like 2 little boxes, maybe. We put the success in the right, because right is right, like correct. It's not a political statement, just in case anyone wondered. And we use left for the error, because it's the only bit that's left. So in code, an either would look a bit like this. Either, pull in some either library, dot right, put a value in, say 5. Oh no, we can start calling map against it, because it's a functor. Like, we get to reuse these things again and again and again. And then what do you get? Oh, you've got a right that's got a 6 in. Either dot left, let's put our error message in, not a number. Oh, suddenly someone's interested. Not a number, JavaScript. Easy way of handling not a numbers. That's kind of exciting. Again, we map it. What comes out, left, not a number. Doesn't even touch it. Doesn't throw an error. We've taken a not a number and tried to add one to it. It didn't even throw us an error. That's pretty good. It's also got these IMAP functions, which let you put a function for running against the value in the left box on the left, function for running against the value in the right box on the right, and then it calls the appropriate one based on what value it has in it. So in this case, if it's got a righty value, it adds 1. If it's got a lefty value, it goes all exclamation marking. Okay, so that's eithers. And what I did, press a button I shouldn't have pressed. What I did at work, at Habit, was I made this error tolerant batch handler. This isn't the exact code, it's really similar though. So I've got my queue handler, takes my array of futures. Future.parallel, put in my limit. It wouldn't be really 5, it would be in configuration somewhere. And then I map over my futures. We're mapping over a list here, we're not mapping over a future. And then I fold my future into left or a right. Okay, so you all remember fold. Fold lets you take elements of a sequence and turn them into one value. Okay, so in the case of a list, we might have a list of numbers, 1, 2, 3. If we fold them all up with the sum value, that come up as 6. So we've turned multiple things into one thing. In the case of folding over a future, we've turned the multiple potential values, success on the left, failure on the right, we've turned them into one thing, which is always a success. Okay? So our futures are always mapped to a success. We're forgetting, we're chucking away the fact that they could fail. But because we've now got an either inside our future, the either tells us whether it failed or succeeded. So we haven't lost the information, we've just hidden it down inside the either. Okay? So now, my list of futures, they're all going to succeed. They're all going to succeed. But they're going to hold that failure or success data inside of their structure. So at this point, I know now that all 5 of my futures are going to succeed, and so I'm definitely going to end up in the positive side of my fork. In that case, I can call a function called value. Value is like fork, but you don't have to supply the error case. You only have to supply the success case. And it gives me my list of either's. So what I can do then is I can extract the successes from them, I can extract the failures from them, I can record back into my database which ones succeeded, which ones failed, I can log the failures, and I'm done. So really, really similar to the code we put into production, this is. So there's a tiny amount of code using simple principles, using this grammar of algebraic data types. I've created simple, reusable system for giving me an error-tolerant queue. I'm really, really pleased with that. So, we're into the conclusion-y part. Should we be using these things? Has anything I've said tonight convinced you that features might be worth a look at? So I think what we want to do is go over some of the pros and cons. Because of the length of this piece and the amount of content I was trying to squeeze in, some of these pros I haven't actually even mentioned yet. So, one thing I have said a lot about is it's got a precise API. It's got this kind of grammar-based API with consistency across different vendors. So whether I'm using Folklore's Future or Future or Data.Future, I'm getting a level of consistency because they all implement map, they all implement chain, they all implement of, they all implement fork, right? We've got that consistency. Next up, it's got great compatibility with all other Fantasyland compliant monads, functors, etc. So we've got that compatibility angle. It's also lazy. So laziness is a big advantage to functional programmers. Big advantage to everyone, really, if you can be lazy. It means that it's a really nice way of encapsulating side effects because they don't start happening until you call fork. And also, they can be cancelled. This is just a straight up efficiency gain. If you imagine if you had a promise.all and a future.parallel or future.traverse, whatever way you want to think of it, if one of those comes back with a failure, it stops, right? You don't care about the rest of the results. In the case of promise.all, all those other 4 still carry on doing the underlying async operation, whether that's talking to HTTP, whether that's accessing the file system. You can't tell them to stop. So from an efficiency perspective, they're doing stuff in your program that they don't need to be doing. Whereas because futures are cancelable, if you've got a list of 5 futures going on and one comes back quickly with a failure, it stops the rest, clears up the resources, just efficient, just an efficient thing to do. So, the pros of promises. Promises are a de facto industry standard. Everywhere you look, you'll see promises. There are lots and lots of, whenever you need to access something where you're waiting for a response, there'll be a promised version of the library. Whether that's talking to a major database, talking to, I don't know, probably the Just Eat API, I imagine, has a promise-based interface. Easier to learn and remember the basic API. Beyond the basics, it might get trickier because it might get very, very specific. But the basic API is just then. Like you've remembered it already. Congratulations. The other great thing about promises is async await syntax from ES8 and Babel. Really, really good for imperative style. Allows you to forget that you're even working with delayed values at all. So if you're writing in an object-oriented or an imperative style, async await is an absolute godsend, and that's all powered by promises. And finally, it's functional enough for most purposes. Promises, when you have an API that uses functions, you get something returned. That's a really good step one if you're a functional programmer. It's a lot better than a callback. You're actually getting a value back. You can pass it around, pass it through functions. A lot of the time, that's good enough. So, in conclusion, do we want to be adopting futures? Well, there's a few different levels of meanings of the word adoption. So, first up, don't use them at all. Just suck up the limitations of promises. Sometimes the error handling is a bit wonky. Maybe you can't cancel them. Maybe that's a bit inefficient, but hey, maybe it's someone else's inefficiency. Option number 2, use them when you need cancellation or another killer feature, like that error tolerance I showed you. If you do this, you might have an ad hoc job to do. So you might look at bits of code of your code base that could be improved by features, and the code surrounding that, you might need to convert all your promises into features. But you won't have to entirely rewrite your code base. Well, the third approach is to go all in. Wrap all of your libraries in a features API and enjoy sweet, sweet sound of coding to real principles and having a real fully functional approach. We've gone for the kind of middle one. We've used features a couple of times when it's made sense. We haven't been zealots about it. But yeah, hopefully a little bit of food for thought, a little bit of an option for you to use. Hopefully you've learned something about why grammar-based APIs might be better than grab bag APIs, and hopefully you all know a little bit more about functional programming though. So thank you very much.